Hello everyone, I'm Liu Yang from DP1. In today's computer lab, we face the problem, the Drunkard's walk, in which we are given a field that can be modeled as an n times n grid, where n is an odd number and the Drunkard is placed at the exact center of the field. The Drunkard then moves one cell in a random direction, including north, south, east, or west, referring to up, down, right, or left on the grid. However, he cannot move to a cell that he has already visited. If he moves off of the field, we say that he has successfully escaped and therefore counts as a success. However, if he moves to a cell such that he can no longer move to a cell he hasn't already visited, we say that he has blocked himself in, which is a failure. In this lab, we will be finding the probability that he will escape a field of given dimensions. For example, the worker blocked himself in this simulation, and in this simulation he successfully escaped. The goal of this lab is to implement a code that simulates the drunkard's walk, estimate the probability that the drunkard will escape in a grid of given dimensions, and eventually plot a graph that shows how the probability changes as the size of the grid increases, and eventually answer the question, at what point does the probability of escape drop below 0.5? My design of the code is divided into 4 functions. The first function, named drawGrid, draws the grid that will be used for visualization of the simulations later on. The second function, named walk, simulates a random walk by the drunkard. The third function, ESC probability, calculates the probability for a drunkard to escape under a certain size of the grid. And eventually the fourth function, named plot probability, plots the escape probability chart given a range of simulations and size of the grid. In the drawGrid function, the function takes 3 inputs, including n, which is the size of the grid, and start x and start y, which are the starting coordinates of the grid in the drawing. The grid is drawn as a set of vertical and horizontal lines using turtle, forming the grid of a given size. However, the grid is drawn slightly larger than n times n to account for the boundaries where the walker may escape to. The walk function takes in 2 inputs, n, the size of the grid, and draw, which is a Boolean value that determines whether or not to visualize the simulation. The function starts off by creating a 2D array filled with zeros, in which each zero represents an unvisited cell. The walker starts in the center of the grid, and this cell is marked as 1, which refers to visited. And then the function checks if the walk can continue by exiting the function if all 4 possible moves, including up, down, left, or right, lead to visited cells. After that, the function randomly picks a direction from up, down, left, or right, and if the chosen direction leads to an unvisited cell, the worker moves there and marks it as visited. If the chosen direction leads to a visited cell, the worker picks another direction until the worker successfully moves. After that, the function checks if the worker has successfully escaped by checking if the worker reaches the boundary of the grid, and returns true if the worker escapes and false otherwise. The escape probability function takes in 3 inputs, including the number of simulations and the 2 inputs necessary for the walk function. It runs the walk function multiple times and counts the number of successful escapes and divides by the total number of simulations. The function then returns the escape probability, which is a number between 0 and 1. Here are my answers to question 3a under 10,000 simulations. The plot probability function takes in 2 inputs, n, which is the size of the grid, and the number of simulations. This function creates a graph showing how the escape probability changes with different grid sizes. The function runs escape probability function for different values of n and records the probability of escape for each grid size. It then uses matplotlib library to create a line graph, where the x-axis represents the grid size and the y-axis represents the escape probability. And finally, a horizontal dashed line at y equals 0.5 is also added to show when the escape probability reaches 50%. Here's the plot that I plotted, which shows that the probability of escape drops below 0.5 at approximately 25 side lines of the grid.